Morning, guys. Yesterday we started introducing some nuclear processes. Again, nuclear reactions are a little bit strange because we may be one element on one side. After undergoing alpha, beta, or gamma decay, we're a totally different element on the other side. We won't be balancing in the regular fashion, balancing the coefficients and whatnot. What we saw was by listing the number of protons, number, mass number, the addition still had to match up. So I'm going to give you one quick practice question for there, and then we're going to switch over. We're going to look back at the Bohr model. We'll see what the electrons themselves are doing as we step towards a newer model over the next couple classes. So let's just do as a quick warm-up here. I'm told cobalt-60 undergoes alpha decay, so the weakest form of radiation. An alpha particle here is a helium nucleus. I'm going to just make up a number here. This may not match up to the actual decay rate, where 40 grams becomes 5.0 grams in 120 days. I want you to find or find the half-life based on my numbers here, and determine how long until let's just make up a number here. 35% remains. All right. So let's just see if we can take apart the formula here. We have cobalt-60, so it's cobalt with a mass of 60. If you look on your periodic table, this may or may not match the exact mass of cobalt. So let me just pull it up here. Cobalt on the periodic table is actually given to you. It is element number 27, 58.93. We're actually doing cobalt. That's fine. It's this form that's radioactive. We're going to do the decay equation here based on cobalt being 60. It's only if I wasn't given a mass, I would round it. Okay, the most stable state was probably going to be 59. So it's cobalt-60. It undergoes alpha decay. We know an alpha decay is an alpha 2,4, where 40 grams becomes 5 grams. That's giving you some numbers to it. They didn't ask you for the nuclear equation, but let's just do it for practice. So cobalt, they wanted you to do it for the cobalt-60, not the most stable isotope based on the periodic table. The alpha decay here is going to be a 2,4. Let's just do the math here. So I had 60 units of mass total. 4 go off with the alpha particle. That leaves me with 56. Cobalt here was element number 27. I had 27 protons. 2 of them leave with the proton with the alpha particle. I now have 25 left over. I've now converted myself over to manganese. That is the alpha decay, and that gives you 40 and 5. I'm just going to practice based on the numbers here. We knew we had a radioactive equation here. Show you a shortcut in a second. So naturally, we want to use this equation. This is the exponential decay formula. This is going to represent how quickly things decay in terms of half-life. And what we would do is you just punch in the numbers. We'd say, okay, I had 40 grams at the beginning. I have 5 grams later on. So this is 5 and this is 40. We have 0.5 as our decay rate. This 120, should that go in for T or the K? This 120 is the actual time that I'm waiting, so that it should actually go in for the top T here. And what we're actually going to do is we're actually going to divide out by K. K is actually the half-life that we're looking for. We're interested in finding that K. So with that, I'm just going to show you the math here. I told you I'd give you a shortcut later on. See if you can think about what that is as we do this. 0.125, 0.5, 120 over K. We introduce having to do logarithms, so pretty much it's a button on your calculator. Press the log button. You can even press the ln button, which is actually a natural log, just to show you that works. I can do ln 1.25. That's the log. Basically, ln is also a logarithm, but the base is e instead of base 10. But in the same sense here, it does the inverse. If you use common log log here, if I, in this case, you use ln here, I use ln here. And because it does the opposite, it just brings down the power. So that's going to now be 120 over K. I'm going to isolate for K here. K would then be 120 multiplied by ln 0.5 divided by natural logarithm ln 1.25. Just pretty much showing you want to use the same log on both sides. 120 times ln 0.5 divided by ln 0.125, and this gives you here 40. Now that looks like a really pretty number. Well, could I have possibly have done it otherwise? I mentioned there was a shortcut. Sometimes they do this to you here. You may have recognized here, what if I did 40? After one half-life, how many should I have left? Well, half of 40 is 20. After another half-life, I have 10 left. After another half-life here, I have 5 left. You'll notice the numbers that they gave you an exact starting amount. the ending amount here is exact 1 whole unit of half-life, you could have actually said, well, this is 1, 2, 3 half-lives. 3 half-lives in 120 days, you could have really easily just said, what's 120 divided by 3? There you go, 40 days. So if it is on an exact number of half-life, you don't necessarily need to go straight to this formula here. Sometimes they try to sort of mislead you with the numbers. It's not obvious that it's an exact half, but you should always check that first, just to save you a little bit of time. Maybe you don't have to do this work here. In this case here, 35%, we're totally out of luck. 35% remains, right? So 50%, the other one would be 25%, 35 would be something like this. The other time here is not actually unit half-life. This one here, I would more so, there's no shortcut for this one. I would just go straight to the formula. On the formula sheet here, NT is N naught times 0.5 T over K. I want 35% to be left over, so I can do NT over N naught. That's my percentage. I need to write this as a decimal because I'm doing math with percent, 0.35. 0.5 T over how long I'm awaiting. Now that I know the half-life is actually 40 days, I can actually use that number. Again, just practicing with logarithms. I use natural log over there just to show you it works with common log as well, so just log. I'm going to bring down the power, T over 40, log of 0.5. Do the manipulation there, 40 log of 0.35 divided by log of 0.5. Let's see what that leaves us with here. T is equal to 40 log 0.35 divided by log 0.5. And this is giving me roughly 61 days, give or take. Right. Again, always do a mental check here. Does that make sense? Well, we had said a half-life was 40 days. So it took 40 days to do this. We wanted to wait somewhere between 40 days and 80 days. Great, 61 seems like a nice number. All right? So just make sure you do your practice worksheets there so you can actually practice the math here. They do introduce logarithm. That's the extent we're going to use for logs. We'll see a little bit more next year, but hopefully by then you'll have enough practice for your math classes. That sort of finishes off our sort of nuclear section. We're going to now focus back on, well, what about those pesky electrons? What about the regular reactions I'm interested in? Valence shell, what about all that? So we're going to totally switch gears here, totally, like, we now understand about the nucleus. Let's focus more so back on the Bohr model. For the Bohr model, they sometimes do call these ones here electron diagrams. So they ask you draw an electron diagram. They're essentially just saying draw the Bohr model. So if you sort of think back to a couple lessons ago here, we had ended off, we had studied sort of the evolution of the atom. The atom has always existed the way it is, but as we get more information, our understanding of the atom changes, our model of the atom changed. It changed from just a Dalton model, right? So solid sphere to plum pudding. No, electrons are actually tinier than the atom. Rutherford came along with the GO4 experiment. No, all of it's actually squeezed into the nucleus. And eventually we hit this Bohr model, obviously in honor of Bohr here. I'm just going to take a look at some random element here. We'll take a look at nitrogen. From the periodic table, you can borrow sort of the two numbers that are important for nitrogen. Element number 7, it gives me a 14.01. At this point, you should be able to tell me here, well, this is the atomic number. That tells me we have 7 protons. Because we're going to always assume things are atomic, things are neutral, the proton number here, so let's just say neutral here, the proton number should match up with the number of electrons. Positive matches electrons. How do I get number of neutrons? We talked about this decimal here, not because of electrons, but this is probably because of weighting of isotopes. Maybe I have nitrogen that weighs 14 and weighs 15, but the 14 actually is much more common. So that's why the average is not quite an exact whole number. For us to have a counting number, I want to have a whole neutron. So I'm going to round that to 14, and I can then say 14. If 7 of those I know have to be protons, how many are neutrons? Well, the neutron number has to be 7 as well. So like we mentioned here, for very light elements, for things on the top of the periodic table, pretty much the proton and neutron number come very similar. They're very close in number, but as you keep going lower and lower on the periodic table, you may be picking up one proton, but there's so much more repulsion between those leftover protons that we actually need neutrons to increase the strong nuclear force to actually make it more stable. We've done that PNE sort of analysis over the last couple of days or so. Today what we want to do is we want to just rehash what are the electrons actually doing? What do they look like when they're actually around this shell here? So again, we've done the nuclear stuff, so I'm just going to draw the nucleus here. The nucleus, is going to be protons and neutrons. I'm just going to list them, 7 protons, 7 neutrons. If I had time, I would actually draw 7 circles for protons, whatever, but that seems good to us. Our nuclear reactions happen in the nucleus. It was this center that did the emit an alpha particle, emit an electron, emit radiation, whatever. Now what we're doing is we're back to regular chemical reactions, and we're actually looking, well, if electrons are in the shells and they mark off the sort of the size of the atom itself, where are the electrons actually appearing? For Bohr, he took Rutherford's planetary system, and basically what we ended up having is electrons can actually end up in any number of orbits around the center. We're actually going to count the orbit number here using a number n. So I'm going to say n equals 1. N equals 1 means the first shell, or the first energy level. And we're going to actually, for Bohr, we're going to have many energy levels. You can think of them as the different orbits for the different planets. For some reason, we're going to see a little bit of Bohr's experimentation. He found that there's a certain limit to how many electrons can actually sit on these shells here. Let me just draw you those quick limits here. So just a quick table. If I'm on energy level, so energy level, it represents sort of the n, the shell number. Energy shell 1, shell 2, shell 3, I'm going to list for you how many maximum electrons on that shell. So first shell, in your junior science classes, you'd say, well, first shell is tiny, it's close to the core, it can only handle 2. So 2 it is. Second shell here, oh, that's farther from the nucleus here, that's going to be 8. The third shell here, depending on who you ask, most people would say 8. Some people would say 18. We'll come back towards the end of this chapter to figure out, well, why is it 8? Why is it 18? When do I say 8? When do I say not? So in this case here, I would say for Bohr model, just stick with the 288. So we're going to use this analogy here. I have my nitrogen sort of drafted out here. Imagine you have 7 electrons that are just sitting on the side here, right? I know I need to add them to the atom. Electrons here, I know they have a negative charge. So given these 2 possible shells to sit in, where should they go? If an electron is negative, that first person arrives, the electron given the option wants to be as close to the core as possible. Because the electron is negative, it's going to jump into shell number 1. We can write that in words here, not super surprising. Electrons always enter the closest shell, so closest to the nucleus, the energy level that's lowest, because of attraction to nucleus. Now, it's not actually going to run into the nucleus. Fortunately for us, it doesn't our atoms implode. It's because electrons actually have some velocity. They actually are moving. It actually keeps it from going to the nucleus. If you use the analogy of the solar system, yeah, the sun is attracting Mercury, attracting that planet. Well, given an option, Mercury would want to just smash into the sun. But the reason why it doesn't is because Mercury is actually in orbit. So there we go. That first electron got in. Now it's time for the second guess. The second guess here also has a negative charge. The second guess also wants to enter the closest shell, but the second guess here has a little bit more second thoughts. Because as the second electron goes in, it says, yeah, I want to be close to the nucleus because the nucleus is positive. That's what I like. And yet that first person has already gone in. That first person is negative. Do I really want to sit with them? So in this case here, as I'm building the atom, there's always going to be these little compromises. We're going to see a lot of this in chapter 3. But in some sense, overall, looking at what ends up happening, the electrons say, fine, I'll squeeze in next to this person here. I might have a lot of repulsion with the person next to me. Electrons hate other electrons, but at least this means I can be close to the core. In fact, this always happens for the Bohr model. Electrons will always enter shells that are closest to the nucleus. What about the next electron that arrives? So the third electron. The third electron also realizes, hey, I'm also a negative charge. I also want to be close to the core. But based on this strange maximum, it says, uh-oh, the first shell here is completely maxed out. In that case there, because it's maxed out, the next closest spot for it is, okay, fine, I'm just going to go on shell number 2, and I'm just going to be somewhere on this outer shell. That's the closest it can get because that first shell here is actually being packed up. Just for simplicity, what we're going to do, first shell holds 2. It's important to draw them as paired because that is actually correct. As the next 5 electrons go on, I'm actually going to add them. The third one went in. The fourth one goes in by himself. The fifth one goes in by himself. Usually for convenience, I just go sort of top, right, down, left to make sure they're separate. You probably remember from your junior science classes, if you happen to have 5 electrons on the shell here, then that 5th electron actually pairs up with one of them. It doesn't matter which one. It could have paired up with this bottom one. In this case, I showed it with the left one. That's fine. That is the correct Bohr model. You can make a note here. Electrons, so I'm writing them as E- just for short. Electrons enter singly They enter one by one. They enter just totally by themselves until pairing after the 5th electron. So we go single, 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 and then, oh, I have the 5th person come in. They're going to pair up with one of them. We're going to carry that into our newer model as well, but there we go. Now you might say, well, I thought you said shell 2 is actually 8. Remember, 8 was the maximum number. Nitrogen just didn't have enough electrons. If you then become oxygen and fluorine that have more electrons, then yes, you can come back and you can pair the rest of them. But in this case here, I only have 2 on the first shell, 5 on the outer shell. This is actually hinting at what's referred to as an electron arrangement. Sometimes people hate drawing circles and it's too much detail. They can draw an electron arrangement, sometimes also called a simple Bohr model. And essentially it's just a listing. I'm going to use by convention inside to outside. I'm going to list how many electrons you have. So in this case here, the simple arrangement, I have 2 electrons in the first shell. I'm going to say 2. I happen to have 5 electrons in the other shell, 2, 5. That's my electron arrangement. Later on in this chapter, we're going to do a new model called electron configuration. That's going to be a whole lot more detailed. We actually need to break up some of these shells into subshells, but notice that's a different language from electron arrangement. Sometimes they even say 2.5, like period 5, but they're just listing for you. Well, for the nitrogen, as I've drawn it, the first shell is holding 2, the second shell is actually holding 5 there. All right. So we have that there. The same thing would happen on shell number 3. Because we're starting to count shell number, the energy level and whatnot, not only is it just saving us, oh, we're not having to draw circles, what we're going to try to transition to is trying to transition from just drawing the electrons in the different orbits. In fact, we're going to learn later on in this chapter they're actually not in orbits, to actually transition this into what's referred to as an energy level diagram. So in practicing this here, let me just sketch up for you another Bohr model. So another Bohr model. Start off with the Bohr model. Let's do sodium as an example. And I'm going to cheat a little bit here. Sodium, we should have actually listed the protons and neutrons. I'm actually hinting at even the Lewis structure here. Later on, we're going to use a symbol to hide all the inner shells. But sodium, again, on the element number, double check my numbers. It should be element 11. I think it's 22.99. I can identify here, well, 11 protons. This mass here needs to be rounded to 23. That would tell me then I have 12 neutrons. So 11 plus my neutron number has to be 12, and that would mean 11 electrons. Fine, I won't be lazy. So we have sodium here. Sodium is going to be element number 11, 12 neutrons. It has actually, every atom has an infinite number of shells, but just like planets in your solar system, if I don't have any planets doing that orbit, there's no point of actually drawing the orbit. So I'm going to make that note here. Elements have an infinite number of shells available. So electrons can be on any of these shells. We'll qualify that a little bit. But I'm only going to draw the shells if I actually have the electrons. So imagine 11 people arrive at this atom. 11 people need to be added to this. I tried to mark off the neutron and sort of the inside here. So this is n equals 1, 2, 3, like that. I'm going to draw in, okay, first shell, 2 of them go on. They go on as paired. Second shell, we go single, 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 and then we go pair, 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 pair. This time sodium has enough electrons. So far I had 2 on the first shell, 8 on the next shell. I still have 1 more to go. I'm going to put the 1 more out here. Shell number 3, n equals 3. Right, n is just the shell that I'm at. N equals 3 happens to have a single electron orbiting outside. That is the Bohr model. The simple electron arrangement would just be 2, 8, 1. It's not 288 because I don't quite have the maximum number yet. But what I'm going to start doing is I'm going to start drawing this on what's called an energy level diagram. On an energy level diagram, instead of plotting the different shells, instead of plotting these circles here, which electrons are actually not realistically doing, what I'm actually going to plot is we have protons in the nucleus. They're going to represent a positive core. The positive core is attracted to the electrons on the outside. There's some amount of potential energy between the positive protons and the negatives on each of these shells here. So what I'm picturing here is, imagine that we have the nucleus somewhere down here. I know the nucleus itself is positive. For these 2 electrons that are sort of shell 1 away from the nucleus, for being that distance away, it's going to have some potential energy being that far of a gap. So what we're going to do is we're just going to mark off here. We're not going to get into all the formulas of it. If you go into the physics, you can actually calculate the potential energy. But I'm just going to say, for being on shell number 1, for being yay far away, we've actually stored a certain amount of energy. This is going to just represent my shell. That's now the energy for being on the first shell. I have 2 electrons on the first shell. I can just simply draw 1, 2, and those are those 2 electrons on the first shell. Now let's compare to the next shell out. The next shell out here is further from the core here. That means the attraction is not going to be as strong. If the attraction is not as strong here, we're going to be less stable. Less stable on this diagram here means more energy. So energy shell 2 is not only going to be farther from the nucleus, it's actually going to have a less stable, higher energy reading. So in this case here, energy shell number 2, I know it is somewhat represented to the distance, right? This is close to the core, this is farther away from the core, but in fact, the farther away from the core, the less stable I get. If I had the time, I would actually draw 8 electrons on the shell here. And so far, I would just keep sketching out from there, shell 1, shell 2, shell 3, depending on where those electrons actually are. We're going to later on sort of modify this diagram a little bit, but we're going to actually see how this energy diagram here is a little bit more precise than the Bohr model itself. All right? Let me just make a note here. There's one other comment I want to make. Elements do have an infinite number of shells available. You'll notice I've drawn sodium here with 3 shells. What about sodium's 4th shell or 5th shell? In fact, sodium does have shell 4, does have shell 5, but because I don't have enough electrons to occupy those ones, it's going to pretend as if they're not there. However, if you read that statement here, having an infinite number of shells, you might start wondering, well, does that mean that this atom here can be infinitely big? If shell 4 is there, shell 5 is here, couldn't shell 6 be here, shell 7, shell 8? Couldn't this atom be infinitely large? We know that can't be the case. We've already been saying atoms are supposed to be really, really tiny. What gives? If I'm supposed to have infinite shells, and I need to couple it to this fact here, and there is a limit to the radius, how can they both be true? How can it be that electrons can be, yeah, I can be on shell 1 or shell 10 or shell 1000, but how can I have a limit to, well, I can't get infinitely far away, because if I get too far away, there isn't enough attraction to actually hold my electrons. Our conclusion then is to hold those 2 things together. That means as I get farther and farther from the core, even though I do have shell 1000, shell 1,000,000, shell a gajillion, whatever, these shells here actually need to get closer together. And that's represented really well with this energy level diagram. As you go farther and farther from the core, you're going to see that your energy shells actually get closer together. So let me just rehash that again. Elements do have an infinite number of shells available, but there is a limit to the radius due to a finite attraction. I only have so many protons. If you're too far away from the core, I can't hang on to you anymore. So in that case there, our conclusion is the energy levels, pictorially, it's like the shells get closer together. More clearly, though, it's the energy levels actually converge. So to hold those 2 things together, elements have an infinite number of shells available, limit. So therefore, our conclusion is the energy, you can say the energy spacings get smaller, but you can say the energy levels, the terminology we're going to use is they actually converge. Converge means they come together at the high energy end. They basically had to stack up. They actually had to get closer together. It's not like this radius here can just keep infinitely getting farther out. We actually see that convergence here. The energy shells are actually closer together as I go to shell 4, shell 5, shell 10, shell 1000. And that sort of puts both things together. Yes, you are allowed to have an infinite number, but you also have a limit to your radius. So the only way to keep those 2 things together is to have those energy levels converge. And it is always converging at the high energy end. It's converging at the outside end. Right? Let's just switch to a quick question on radii. Switch to a quick question on just the sizes of atoms. This will come up a lot in our next chapter, but let's just touch on it here. I want you to arrange, I'm going to list for you 3 species here. Arrange by increasing radii. Arrange by increasing size. So that means tell me from smallest to biggest. I'm going to give you a second. See if you can draw the Bohr model. Draw me fluoride, draw me sodium plus, and draw me neon. Right? Maybe you can pause the video and you can see how you do. So for fluorine, you can check the numbers. 9 protons, 10 neutrons. You're going to find that fluorine is supposed to have 9 electrons, but because as it's negative, fluorine actually happens to have 10 electrons. So where do the first two go? First shell. Where do the next two go? Next shell out. Single, 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 single. Pair, 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 pair. Just like we did for ionic bonds previously, because it's charged, I'm going to put a square bracket around it with the charge. This is minus. What I've chosen for you is actually 3 things that actually all have 10 electrons. Sodium was supposed to have 11, but having become positive, it's now lost that electron. It's been oxidized. Neon is a noble gas. This one here is also 10 electrons. Just having 10 electrons means your electron arrangement is supposed to be, for all of them, it's supposed to be 2, 8. 2 on the first shell, 8 on the next shell. Does that mean that they're the same size though? So let's say for sodium here, so sodium should have had 3 shells. It should have been 2 there, single, 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 pair, 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 pair. Sodium should have looked like this, but upon becoming the +1, it lost this electron. The second that I lose the electron, there's no point in drawing that shell anymore. Again, I also have 2 shells, but I'm positively charged here. Neon here, probably the simplest. Neon was a noble gas. So neon just happened to have 10 electrons. It also has 2 full shells. The question, however, is just because I look alike, just because I have 2 on the first shell, 8 on the outer shell, I want you to know this terminology here. Although these species are, here's another ISO word for you, they are isoelectronic. Again, remember when we saw isotope, iso means something is the same. This time, the thing that's the same is they actually have the same arrangement. They actually have electrons in the same orientation, 2 in the first shell, 8 on the next shell. But just because I have 2 shells, I look alike, doesn't necessarily mean my size has to be the same. As I've tried to roughly draw for you here correctly for you, what's happened here is I can have 2 shells and I can be yay big. I can have 2 shells and I can be tinier. Even though the electrons are occupying 2 and 8, my shells can still be the same. They can still be different distances. What does the distance depend on? We sort of alluded it to in the last statement here. It's the attraction to the nucleus. You only have a limited number of protons. I have 9 protons that are attracting in these shells here. That's not going to be a really strong attraction. As I go from fluoride to neon, neon actually has 10 protons. Sodium actually has 11 protons. So be really careful. 2 things are happening here. The nucleus itself is getting larger. The center of it is actually getting bigger because I'm getting more protons, picking up more protons, picking up more neutrons. But when I talk about a size, a radius, I'm not measuring just the size of the nucleus itself. The core can big all at once. All I really care is, wait, sodium actually has more protons than fluorine does. Because sodium has more of a positive attraction, it's going to actually manage to pull its 2 shells in a lot tighter to the core than compared to fluoride. So that's actually what we see. We'll do a lot more of this in chapter 3. But basically here, arranging by increasing radii, I should say from smallest to biggest, the smallest should be the one with the most protons. It should be Na plus is smallest, then comes neon, then comes fluoride. They all are isoelectronic. They all look alike. Although species are isoelectronic, we can make a note here. Sodium plus has the most protons, so it has 11. That means it actually has a bigger nuclei. Right? But again, we're not really worried about the size of the core. We're actually saying now, because I have those 2 extra positives, that means you're actually going to be able to pull in your shell even tighter, closer to the core. So sodium plus here has more protons, it has a bigger nuclei, and it ends up pulling in the shells tighter. Na plus has most protons and pulls electron shells tightest. And our conclusion there is it would therefore have the smallest radius. It would have the smallest size because it has the most protons. So when we talk about radius, we're talking about from the center. I didn't introduce this to you yet, but it's from the center to the outermost shell. The name for the outermost shell here is the valence shell. So outermost shell, this is the valence shell. And it's actually your valence shell that actually does all the bonding. If you want a name for the other electrons, you can call those core electrons, be it they just come along for the ride. I'm just going to make one last little note here, and then we'll pick it up from here tomorrow. When we start, especially drawing this on an energy level diagram, basically plotting how much stored energy these electrons have relative to the core, noting that they're coming together, we actually realize, wait a second, if electrons are just particles and they just have to be somewhere around the nucleus, Why is it they have to be on shell 1 or shell 2 or shell 3? Couldn't they actually be on shell 1.5? Couldn't they actually be this distance or this distance or this distance away? In fact, we're going to repeat one of Bohr's experiments to actually justify what he found to sort of explain his predictions here. Is he found, for some reason, when you do these energy level diagrams, so we'll end off with this conclusion here. For an energy level diagram, we have a big energy axis on the outside. Roughly, you can think about sort of the distance from the nucleus. You can say this is shell number 1, shell 2, shell 3. The shells actually get closer together. What he ended up realizing was these shells are actually discrete. So electrons, sure, they could be on step number 1, they could be on step number 2 or step number 3, but there was no in between. Like a staircase, you can't stand at step number 1.5. There's no place to put your footing. So again, I'm sort of doing this backwards here. I'm giving you his conclusion, and then tomorrow we'll actually take a look at what did Bohr do to actually get this conclusion. So what I want to take away here, energy level diagram, what we're going to say here is these shells, energy shells are, the terminology is quantized. Quantized just means they occur in little quanta, little packets. Another terminology here is we can say energy shells are quantized and discrete, meaning they are at unique energies. Every element will have different energy levels, different energy spacing, because they have different number of protons. But because they're quantized, because we're more like a staircase, what can then happen is as electrons jump up and down the staircase, because they can't land and they can't stop anywhere in the middle, every time they jump a certain staircase, they're always going to traverse a certain amount of energy. So energy shells are quantized, they're discrete, unique energies. There are no in-between energy levels. Right? So there's no in-between steps. There's nowhere to land here. So therefore, every time it jumps the gap, it always corresponds to a unique energy gap here. I'm just going to introduce to you the language that we're going to see more in tomorrow's lesson. Why do electrons actually jump up and down? It depends on your experiment. You can actually provide an energy. If the energy is exactly the unique energy that it needs, I can actually send in energy. Hopefully we can do this lab here. Using electricity, this electron can grab the energy and actually jump to a higher energy state. But it has to be a really unique energy corresponding to how big this staircase is. So let me just write this down here. We'll call that process here absorption. That's one big word that we're going to use in chapter 3. For absorption, electrons can, well, like we said, absorb energy. Electrons can take in energy. As they grab more energy, they can temporarily jump to a higher energy state, jumping to a higher shell. Right? So that's like, okay, send in electricity or send in light. If it's of the right amount, this electron can steal that energy and jump to a higher energy state. It can be on shell 2, even though there was a spot more stable than it. So it can jump to a higher shell here. Basically, I can draw the diagram. It's like taking an electron down here, and it can jump up to some higher shell. But we are a staircase, so we have to still land on a certain step. It dances around for a little while here. Right? It doesn't really want to stay there. There are spots that are closer to it. That would actually be called an excited state. Right? Because the electrons are more excited, are farther away from the core than they need to be. Eventually, the opposite process here is the emission. This is the one we're going to do more in tomorrow's lesson. Electrons, after temporarily being in that excited state, electrons can release energy. They can give back this energy. And the terminology we're going to use is falling to lower shells. And we're going to do this more in detail tomorrow. As it falls, depending on which shell that actually falls to, it's going to try to fall back to your ground state. It's going to try to fall back to your lowest energy state. And in some sense here, because of the energy shells, because of the energy spacings, as this electron, the electrons are stuck on the atom. It's not like they can leave. But as the electrons get closer back, this is shell 1, shell 2, shell 3. As they get back to shell number 1, they end up having to release the energy. And Bohr actually did this, figure out what this energy looks like when it comes off, and actually rationalize all this here. He derived this notion, yeah, elements are weird. Energy levels are actually quantized based on the experiment we did. So I'm sort of hinting, this is the conclusion we're going to take away, and in tomorrow's lesson we'll see what sort of experimentation sort of justifies this. So we'll pick it up from there. Thanks, guys.